looks like we are ready to start again. So when I sent out the call for presentations, one of the first ones to reply was Solid Designer. As I just presume that all of you now know who he is. And he replied to me and said that, well, he had somebody who could talk about implementing bcrypt in FPGAs, and he asked me if I would be interested in having that at the conference, and I said, yes, please. And when Katja arrived on Saturday, I had to say I'm really sorry, because when Solar suggested somebody to talk about bcrypt implementations in FPGAs, I just assumed it would be a boy. Forgive me, girls. So I said I'm sorry to Katja when she arrived, because to me Katja is a girl name, but still I really couldn't believe a girl would do such a talk. Sorry. But this is Katja Malvoni from Croatia, and I will let you do the rest of your own introduction. And good luck.
Thank you.
Yeah.
Thank you. Hello, everybody. So today I will talk you about a bit different approach to bcrypt cracking. I will talk about energy efficiency. So as you can see here, bcrypt is not, well, it's not friendly to different hardware platforms. So when you see all of this, you can ask yourself, why even bother? Let's just drop it. People who invented bcrypt did very good job, so what should we do? But we have all of these devices. Each of them has a different characteristics that matches bcrypt specialities. So you will see later during this talk that every of these devices, as Parallel, Epiphany, Zboard, Xeon Phi, Haswell, have different things that match or don't match bcrypt as hashing algorithm. So bcrypt is based on Blowfish block cipher. What is special about bcrypt is its user-defined code setting, where user can control difficulty of computation. Another thing that makes bcrypt difficult to implement on some platforms are pseudo-random memory accesses. And the last thing is memory usage, where we have 4 kilobytes for storing S boxes and 72 bytes for storing P boxes. It's important to say that for historical reasons, cost used for bcrypt is 5, and all figures used in the talk will be for that cost setting, but it's not recommended to use it for protecting your own system. It should be higher, such as 10 or 12. Blowfish encryption is actually has 64-bit input blocks with the Feistel network. It works like this. This F function loads data from S boxes. A, B, C, and D are 4 bytes of L, with A being the most significant one and then to the least significant one. And this pseudo-randomness comes to the point when with 32-bit loads from S boxes. Expensive key scheduled Blowfish algorithm in its states initializes X boxes with digits of number pi, and then with expand key, all 3 of them, what they do is they replace P boxes and S boxes 2 at a time. So every of these expand keys does bcrypt encryption 1042 times to replace all entries in the P box and 4 S boxes. The most costly part of this algorithm is this repeat 2 of the power of cost, where this expensive expand key is repeated over and over again. Bcrypt algorithm itself uses expensive key Blowfish setup, and then the states that return with this part is encrypted with the following string, and returned as a hash. So the first implementation I will be talking about is an Epiphany chip, which is part of Parallella board. Epiphany architecture is very friendly to bcrypt because of bcrypt's sequential nature, and it's also energy efficient. It has 32 kilobytes of local memory, which is more than enough to storing 4 kilobytes of S boxes and some bit more for P box. There are also 64 register, floating point unit in integer mode, load store instructions that load and store double words, and it's interesting that it's possible to directly address core's local memory. There are also some problems because FPU in integer mode can execute only add and mul instructions, and for bcrypt we need XORs and shifts and stuff like that, so more logical than arithmetic instructions. Problem is also there are only simple addressing modes, so we need to use more registers than, for example, on 86 architecture, where there are index scalings. So this is how Epiphany looks like. There are 64 chips with 3 different network or chips used to route the data, and it has local memory. These are just numbers of consumption and performance numbers. So this is how it all started, somewhere in June. First algorithm was written only in C, and first working multi-core code had performance of 822 cracks per second. And I still remember that moment when the thing actually worked. And I was so happy to see it working that I didn't care about performance. It works. And then after all that enthusiasm, someone showed me, well, other bcrypt performances, and I was, oh, well, at least it works. So the next optimization was to move all code to core local memory, so that there aren't stalls when trying to fetch instructions for external memory. That resulted with a speed up to get a performance of 930 cracks per second. And then that was the limitation of the architecture. Compiler wasn't able, even though we specified we want FPU in integer mode, compiler wasn't able to actually do the scheduling and produce the assembly code that actually uses both FPU and integer ALU. So the next step was to write assembly and to use dual issue. What you see behind is actually instruction scheduling. Yes, it's written on paper, because first attempt was slower than compiler-generated code, and next few attempts as well. So I just decided to write it on paper, count cycles, mark when it's fine, when there are no latencies and stuff. So after lots of trials and errors, finally dual issue was used successfully, which gave performance of 976 cracks per second. Then one bcrypt instance running on a single core doesn't have enough parallelism to fully use the dual issue architecture, because there are 4 cycles latency when using FPU. So we needed to add another bcrypt instance to bring enough amount of parallelism so that we can actually use dual issue even better. First thing was to do it in C and see how will it compiler be able to do something on its own, where it wasn't really. Performance is less than optimized single instance core. Then we did preloaded of PRIs, because it's used in every iteration of replacing S-box entries. And compiler was fine with preloading that in 36 registers. So the performance was almost 1,000 cracks per second. And the last part was to do the same scheduling as it was done with one instance. So just do it with two and exploit as much parallelism on instruction level as possible. This resulted with performance of 1,200 cracks per second. And we had 227 emails on John Dev mailing list to finish this implementation. So this is the assembly part of implementation. So these TMP A and B are for first and second instances, and they are interleaved to have enough to cover latency for using FPU. Those email and EAD instructions are actually executed on the FPU. So for each of those, we got one cycle free because we were able to execute two instructions in one cycle. Another very useful thing on Epiphany are double loads, where we were able to do it in half of cycles that would need if there would not be double loads. So in total, we have 2 bcrypt instances per one core. We optimized it in assembly, used dual issue architecture, and integrated in John the Ripper. So this is how it looks like. This is for Epiphany with 16 cores and for Epiphany with 64 cores. This is efficiency of architecture. It's 600 cracks per second per watt, because Epiphany TDP is 2 watts. But even though there are some, even though architecture isn't Epiphany is very bcrypt friendly, but its problem is that the FPU can only issue 2 types of instructions that we actually needed. But nevertheless, we achieved very good performance when compared to full integer dual issue architecture. On Epiphany 64, the performances are almost 4 times bigger than on Epiphany 16. So we have excellent scalability with 99.7% efficiency. And the only thing we changed in code to run on Epiphany 64 was this. Actually 2 times, one on host side, one on Epiphany side. So it's also very portable code. And this is how the system looks like. So it's actually FMC, which can have either Epiphany 16 or 64 with a Z-board. The next platform we used is Z-board with its dual ARM Cortex processor and FPGA fabric. This architecture is interesting mostly because of FPGA fabric. So the first thing was to implement communication between FPGA and CPUs, which is done in the following way. So we have a Cortex here with its slave and master port. We use DMA to get all the data into shared VRAM. Bcrypt reads data from shared VRAM and communicates with the Cortex on this master-slave port, where Cortex can read software-accessible registers in bcrypt to control the state machine, to control actual beginning of computation and to wait for the end of the computation. So first implementation was 5 cycles per round, done as is summarized here. So we do first implementation was 13.9 cracks per second on actually using only one bcrypt instance, only one bcrypt finished state machine. And we used shared VRAM as shown on the previous slide. So it's dual port RAM, but DMA is connected to one and bcrypt to another, so we were able to use only one BRAM port to actually read the data, which made this implementation really slow because we had to wait for the data and actually read it 4 times. So the next optimization was to copy S boxes into local instances where we can use both ports and thus have 2 lookups in one cycle and then compute new L and R. With this approach, we were able to fit 14 cores with a performance of 311 cycles per second, cracks per second. Then we optimized that to 4 S-box lookups at one cycle. The next cycle, we wait for data from the BRAMs. To do that, we had to split data in actually 2 different BRAMs, where we have 2 S boxes in one and 2 in another, so that we can use in total 2 ports for each one, and in total have 4 S-box lookups. So at single core speed, we have 79 cracks per second. It still fits 14 cores, so it's 780 cracks per second. In theory, this would give this number for performance, but there are overheads of actually computing part of bcrypt hash on ARM processor, because only 2 to the power of cost a loop is implemented in FPGA. In total, this works for 2 cycles for 5-cell network around, and the course runs at 100 megahertz. And here we have overview of utilization. There are rooms. So this is performance. Performance per watt. The second figure is only for FPGA, and the third one is for whole system with Z-bars. So counting ARM cores consumption as well. There is a lot of room for improvement for this implementation. At the moment, LUT utilization looks, well, insane. It's too high. We should be able to fit much more cores on the Z-bar at the moment. There is problem with support logic. Support logic is DMA, 3 axibuses, and all is initialization done to actually copy data into per instance S boxes. So we also need to reduce that, because 1/3 of board being consumed by that, it's too much. We also need to consider some designs. At the moment, there is only 1 finished state machine per core. We need to try interleaving more of them to use the logic better, so have 2. And there's also since we don't have problems with block RAM utilization, there is also opportunity that we can use only 1 S-box per BRAM, so that with 1 port we access only data only when doing computation, and with the other port we access data when initializing the S-boxes and when reading the data. And also we need to improve communication, because it determines the longest path, so it determines clock cycle, clock frequency, and it took away 1/3 of the port. So the next architecture that's interesting is Xeon Phi. It's interesting because of its vector processor unit, where we can execute 1632-bit integer operations per clock cycle. And we have 60 cores, which each of cores supports 4 threads. So what we tried first was to use only scalar units and to build John the Ripper with OpenMP and OpenCL, which resulted in these performances. And next step was to use a vector processor unit. For that, we had to be careful to stay that memory usage stays below cache L1 data cache size, which is 32 kilobytes, because if we exceed cache size, we won't have data ready in the next cycle when doing SBOC lookups. We also, because of that, we need 4 kilobytes for S boxes and 72 bytes per P boxes, which give us 7 instances running per core. So we tried all that, and with all possible combinations, this was the one that resulted with highest performance. So not exactly what we expected, because although gather loads exist, they don't tend to show us, they didn't help us to improve performance. So we also tried Haswell with its AVX2 intrinsics. The first code was written by Steve Thomas with the following performance, but it was exceeding data cache size, because it was using 8 instances per core, which is more than 32 kilobytes. So we tried to stay in cache and to reorganize the code. So we reorganized, changed memory layout, and using 7 instead of 8 instances, which resulted with this performance. But non-AVX2 code in John the Ripper is actually much faster than using AVX2 and its gather loads. So we can conclude that the loads are just slow, and we hope that the future CPUs will do better. Power consumption, we divided we grouped similar devices together. So for CPU, we can see some impressive figures for performance, but the efficiency is very low for all of them, because Bcrypt is moderately unfriendly to today's CPUs. These are full system power consumption figures. Well, this table is more for you to look at it than for me to read it. So I'll just go over those. We have the same for GPU and Xeon Phi. So again, you can see some nice figures, performance, but very low efficiency. And then we have our energy efficient platforms with much improved efficiency figures and performance, which is a bit lower. So how it looks like when we compare similar lithography. So we are comparing Epiphanies to x86 cores. We can see that all the performance is pretty much the same. Efficiency is much higher on Epiphany platforms. That holds true for Epiphany with 16 cores, and here for Epiphany with 64 cores. In total, what we have, again, we see for Xeon Phi, GPU, and CPUs that performance numbers are high while efficiency is low. But for Epiphany, it's still a nice performance comparable to CPUs and much higher energy efficiency. So I have a short demo here. I brought the Z-board with me. And here I'm demoing integration with John the Ripper, and more depth than speed. So, what? No, it's connected with USB and it's too short.
Just hold it up then.
Okay, so I have here a fake hash file with a password list for Z-board. For Epiphany 16. at the end for Epiphany 64. So this one is done already, and we still have to wait for the other two. So ZBoard is also done with performance of 761, and Epiphany 16 as well. So for the future work, for parallel Epiphany, what's very good about this architecture is the fact that it has chip-to-chip links for integrated up to 64 chips on a single board. If we use that with 64 chips, with 64 cores, we get theoretical performance of 300,000 cracks per second, which is really nice figure, but it's only theoretical interpolation. But scalability and portability of current implementation is really promising. For FPGAs, what we plan to do is to do all these ZBoard optimizations mentioned on what room from improvement slide. We plan to target bigger FPGAs and multi-target FPGAs boards such as ZX with 4 Spartan FPGAs. And what I'd like you to remember is that multi-core low power risk platforms are a nice match to Bcrypt hashing algorithm, and are able to achieve a very high energy efficiency. What's also important that higher energy efficiency enables higher density, because we can have more chips per board and thus more boards per system. And we did all this and we didn't use ASICs. And we still got energy efficiency that's by a factor of 10 plus bigger than on some other platforms. But all the ASICs would do better. I'd like to thank to Seat and Data for writing first Bcrypt OpenCL code, for Steve Thomas for writing first Bcrypt code that uses AVX intrinsics, to Parallella project for providing us access to Parallella boards, and to Google Summer of Code. Any questions?
Really? No questions?
Yes.
What do you think? Is it possible to make some changes in Bcrypt to increase difficulty of working? I mean, is it possible to change or add some extra parameters or variables or maybe multiplications to decrease efficiency of your implementation?
So question was, what do I think if it's possible to change Bcrypt and add another parameters or computations which would decrease efficiency of my implementation. So for Epiphany board, if we, for example, add couple of instructions that FPU supports in integer mode, then we'd get even more parallelism on instruction level. So it might be possible to reschedule instructions so that FPU saves us because of saves us cycles we would normally use for computing modification. But if those modifications would be logical instructions, then we would have a problem, because we don't have we can't use FPU for that. It had to go on an arithmetic unit and would add additional cycles. And for FPGA, since current utilization is really high, I think anything there would reduce with lower Bcrypt core count, so it would decrease efficiency. As to energy efficiency, these systems that we used have really low TDP of 2 watts for Epiphany chips and something like that for ZBoard. So energy efficiency would stay really high as it is now.
So first a comment in the future work you had, porting that to an FPGA cluster, and a PhD student in Bochum is actually doing that right now. We have a cluster of 128 FPGAs, and he's implementing bcrypt on that one. So you should talk with each other, I guess. And the other thing is, the real question is, can you say something about the prices of the hardware? I mean, it's nice that the energy efficiency is good, but what about the prices?
Actually, prices are excellent. You can get, repeat the question. The question was, can I say something about the prices of hardware we use? So for parallel boards, the simplest model is $99. Then biggers are $199, so very cheap. This Z board I have here is around $400, so USD dollars. So it's still very cheap. But some other things hardware we use, for example, Intel processors, which achieved very high efficiency, but low energy efficiency, cost around $1,500 US dollars each. So our platforms are actually low cost.
I would like to look into how increasing the workload in bcrypt affects your numbers, or affects how many cracks a second you can do with your hardware.
Yeah, so we tried the question was, have we tried increasing the workload of bcrypt and see how it affects performance numbers? So we tried bcrypt for cost 12 and 14, and then performance decreases, so it's scalar. And, but efficiency is much higher because communication overhead and other overheads reduce, because in bcrypt what takes away most of the computation time is 2 to the power of cost loop. So with increasing load, we actually get better efficiency, and power consumption stays roughly the same. Although on desktop systems with CPU and big coolers, the fan consumes a lot of power, so after 50 seconds or so, power consumption goes up because of additional power used to cool the system. But for our platforms, that's not the case. They do not overheat like that.
Could you explain why the GPU-based implementations have so poor performance?
The question is, can I explain why GPU implementation has such low performance? So it's because bcrypt asks for a lot of memory, so it's 4 kilobytes per instance, and it needs that memory. It accesses it sequentially, cycle by cycle. So local memory we have on GPU has latency of 10 or so cycles, which is too much for efficient bcrypt implementation. So we need everything to fit into data cache. And on GPU, it's very small. So we underutilize GPU. Maybe 1/4 of it, it's actually used to compute bcrypt, and that's why the performance is so low.